Welcome back. The objectives of this video are to explore the inverse of a matrix. We'll do a couple samples with that. We'll show an example using the TI-84, and we'll also present the inverse of a 2x2 matrix. The number a raised to the negative 1 is called a multiplicative inverse because a to the negative 1 times a equals 1. So we remember that a number multiplied by its reciprocal is 1, and that's really what we're doing here. So if we let a be some n by n matrix, and our identity is also an n by n identity matrix, there's going to be a matrix a to the negative 1 such that a matrix A times its inverse equals the identity, and the inverse times its matrix A equals the identity. What do we mean by that? A matrix multiplied by its inverse is the identity. So here in sample 1, we want to show that B is the inverse of A, where we've got matrix A and matrix B. So what we need to show is by multiplying matrix A times B, it's going to equal the identity, and we also have to show that B times A equals the identity. And our identity matrix here has to look like this with zeros and ones. Here's our identity matrix. So our solution is as follows. So using our multiplication of matrices properties, negative, essentially the top row times this column, so negative 1 times 1 plus 2 times 1, etc. We've multiplied the matrices and we simplified and we get the identity. And then we did the same thing for B times A. Again, we multiplied 1 times negative 1 plus negative 2 times negative 1, and so forth. We went through our multiplication process, and sure enough, we got our identity again. A times B equals the identity, as does B times A, and that checks out. Those two are inverses of each other. But not all square matrices have inverses. Now we're going to move on to finding the inverse of the matrix. The previous sample was pretty easy because I gave you both matrices. Now we've got a matrix A, but we don't know what the inverse is. We've got to find that out. Our solution here is to have a matrix of the same side, but essentially assign it variables, right? So A times some matrix X is going to equal our identity. Okay, so we need to find the inverse here. So our matrix was 1, 4, negative 1, negative 3. And then our x's in our unknown matrix, we're going to use the subscript for rows and columns. So x11 is row 1, column 1, x12, row 1, column 2, row 2, column 1, and row 2, column 2. So those are all our unknowns with subscripts. And what we do is we simply follow that multiplication process again. 1 times x11 plus 4 times x21 would be our one spot in our new matrix. And then we would repeat that process. 1 times x12 plus 4 times x22 was going to be this next spot in that matrix. And so now we know that since the spots are equivalent, that x sub 11 plus 4x sub 21 has to equal 1. We know that x sub 12 plus this has to equal 0, right? The positions all need to match up. Well, what's interesting here is we've got our subscripts all match up, very similar to a system of equations. We can put that together, equating the corresponding entries, you obtain the following two systems of linear equations. We match up our subscripts and we come up with our two systems of linear equations, and then we can convert those into matrices. The top one here is the augmented matrix 1, 4, 1, and negative 1, negative 3, 0. Well, if I do some row operations, and if I add row 1 to row 2 and rewrite my matrix, I get 1, 4, 1. That still stays the same, but 1 and -1 become 0, 1, and 1. And I can see here, by using back substitution, that x sub 2, 1 equals 1, and then substituting 1 in to the other equation, I can get x sub 1, 1 has to equal -3 to make that equation work. So now I've got a couple spots in my new matrix. Now I can do the same thing with the second system. So rewriting that as a matrix, 1, 4, and 0, an augmented matrix, and -1, -3, and 1, and doing simple row operations, I can add row 1 to row 2. Row 1 is going to stay the same. Row 2, though, becomes 0, 1, and 1, my second matrix. So now I know that x sub 2, 2, which was this spot right here, is equal to 1. And I put that in. 4 times 1, x sub 1, 2 has to equal -4. My new matrix, or my inverse matrix, is our new matrix, -3, -4, 1, 1. So we have solved for the inverse matrix. We can also use our calculator and play around a little bit with inverse matrices. It says most graphing utilities are capable of finding the inverse of a square matrix, and we're going to try and do this with our graphing calculator. So I open up my graphing calculator, I get a blank screen, and I go into the matrix menu. Second matrix, I'm going to use matrix A here, and I'm going to edit that one. I don't want a 3 by 33 matrix. I just want it to be a square matrix that's 3 by 3. And I can start inputting my values and across my rows. 2, -3, and -1, 2, -1. And my final row, -2, 0, and 1. Double check that you've input everything correctly. It looks like it took me a couple tries here, but I eventually have gotten that. And now I can quit. And now I have my matrix. And it says after you find, it's asking me to find the inverse of A. If I go ahead and pull up my matrix, I selected A. All I have to do is use the inverse key, the x raised to the -1, and enter that. And that is the inverse of A. And then I'm instructed to store that as B. So I go to the lower left-hand corner here. I'm going to store it as matrix B. So now I have stored that as matrix B. And then it's asking me to multiply A times B and B times A. So I can select my matrices. So matrix A, go in and select matrix B, multiply them together, and I get the identity. Now it's asking us to multiply B times A. Select matrix B, select matrix A, multiply them together, and again, we get the identity. So a little bit of playing around with our calculator with matrices. Our final objective here is to find the inverse of a 2 by 2 matrix. Using Gauss-Jordan elimination to find the inverse of a matrix works well for matrices of 3 by 3 or greater. For 2 by 2 matrices, however, many prefer to use this formula as it's quick and simple and easy. So if we have a 2 by 2 matrix, matrix A here, think about our positions in rows and columns, and we'll just put our positions as position A, B, C, and D. A is invertible if and only if A times D minus B times C does not equal 0. So what I think of here is I say, think cross-multiplying within your matrix. Think cross-multiply with subtraction. Multiply on our diagonals. A times D minus C times B. And it can't equal 0, then we know we'll have an inverse. And there's a formula that gives us the inverse. So the inverse is 1 over the A times D minus B times C, this particular value here. And then what they've done is flipped A and D within our matrix here. So the D and A switch positions, and then the B and C stay in their same positions, but they take on the opposite sign. Within your matrix, I would say flip A and D, and then take the opposite of B and C. Now, one thing that's interesting here, that multiplying the diagonals AD minus BC, this value is called the determinant of a 2 by 2 matrix. So our scalar here is really 1 over the determinant of our matrix. So that's what our scalar is. So if we want to find the inverse of a 2 by 2 matrix, let's go ahead and do a couple samples. I'm going to start with sample B first. We've got our matrix B. First thing I'm going to do is calculate the determinant. So AD minus BC, we get 3 times 2 minus -1 times -6. That equals 0. We can't find an inverse for that. So that's not going to work. So that's the only value that we can't have. So now we can go on and do A. Find the inverse of matrix A. Remember our positioning, A, B, C, D. So first thing we want to do is find the determinant. 3 times 2 minus a -1 times -2. So that becomes 6 minus 2, which is 4. We've got our determinant. Now, all we have to do is flip the 3 by 2 and then take the opposite of those and multiply by the scalar. Because our quantity is not 0, we've got an inverse, so here is our determinant, is our scalar. We're going to multiply by 1 over 4. The 4 here goes there. We flipped our A and D, we took the opposite, and then we scaled it, and we get our solution. Another real quick sample. How easy is this? Our determinant equals 5 times 4 minus a -1 times 3. Our determinant is 20 plus 3, or 23. Inverse of A is going to equal 1 over 23 times, flip my A and D values, take that 3 and make it negative, I take the 1 and make it positive, and I go ahead and scale my matrix, and we get 4/23, 1/23, -3 over 23, and 5 over 23. And that is our new matrix. And we'll get some more practice with this when I see you in class.